Society of America. I'll read a brief bio, which I should have had in front of me. So Bracken is the Senior Projects Engineer at Stillwater Mine in Nye, Montana, the owner and principal engineer at Alpine Consulting and Mining Engineering. He is a professional mining engineer and project management professional. Bracken graduated from the Colorado School of Mines with a BS in mining engineering and Montana Tech with a Master's of Project Engineering and Management. Bracken began his career at the Henderson Mine in Empire, Colorado, and moved with his family to Montana in 2007, where he began work for the Stillwater Mining Company. Before moving into engineering, he worked first as a miner in Colorado and Montana. So I think Bracken knows what he's talking about. I will turn the time over to him, and please give him your attention. Thank you.
Thank you, Mick. I do appreciate the introduction and the opportunity to be here. Going to go ahead and share my screen. All right, I believe we have that coming up through. So for the next 20 minutes or so, I will be talking about the Stillwater Mine splits, sand plant, everything that went in with the design, development, construction, and commissioning thereof. Being that Sibanye-Stillwater is a publicly traded company, I have in front of you all the legalese, which covers the it has the this may have forward-looking statements, so don't use this presentation to make financial and investment decisions within the company. A little overview of who Sibanye-Stillwater is. Sibanye Gold started back in 2011, was a spinoff of the Goldfields operations in South Africa, primarily gold and platinum group metals in South Africa and then Zimbabwe. From 2011 on, they did tremendous work in turning their properties around. In 2017, I believe they acquired Stillwater Mining Company, located primarily in Montana, along with projects in Marathon, up in southern Ontario, and then in Argentina at the Altar property. So we're a large precious metal company located all across the globe. Tremendous market capitalization, and this screen just shows a really quick snapshot of who we are. So the Stillwater Mine is located in the Beartooth Mountains of Montana. The picture on the top left corner of the screen is an aerial shot of the mine in the springtime. You can see what the surrounding locale is. As the crow flies, we're about 34 miles from Yellowstone National Park, about 90 miles southwest of Billings, Montana. A little overview of where we are located. It is a pristine country. The Stillwater Mine is 3 miles from the Absaroka Beartooth Wilderness, which is the largest designated wilderness in the country. The picture on the left is a great view of where the mine is. The valley that runs back into the mountains is the Stillwater Valley. The Stillwater Valley itself is a blue ribbon trout stream. And with the picture on the right, you can see where the river actually runs right through the middle of the mine property itself. The mine is located both on the east and west of the river, and we do go underneath the river. We are a testament that you can mine in close proximity to pristine and sensitive environments with a great degree of success, local and social interaction, and great environmental responsibility. As we go from the 30,000-foot view into more of who the Stillwater Mine is, we are a cut and fill operation utilizing primarily overhand and underhand ramp and fill mining methods. The graphic on the right shows a overview of overhand mining methods for those who are unfamiliar with it. Overhand mining, which primarily what we talk about in the course of this presentation, is the placement of coarse fraction of mill tails back underground for the purpose of backfilling mined out stoping areas so that we can mine back on top of there. We have moved over the last 25 years from jackleg mining and slushers for moving the broken material to 2-yard LHDs and electric jumbos. So we're on the reef where we are producing the ore. We're typically taking 8-foot wide, 9-foot deep by 10-foot high rounds. We do also use underhand mining techniques with a placement of paste. And in the future, we're going to be looking at using cemented sand on certain areas of the mine as well. In 2012, we began an expansion project. The expansion project is what we referred to as Blitz. It was a large expansion on the east side of the mine. It consisted of running a 18-foot diameter tunnel boring machine, 25,000 feet to the east on the 5,000 level, and then a conventional drill and blast drift 600 feet above there. That area was going to be a significant increase for production for the mine. During that, though, we had the understanding that we were not going to be able to backfill that area with our existing setup. It was beyond what the effective delivery envelope from our current plants and pumping locations were. So we knew we were going to have to both increase the envelope and put forwarding stations as part of the expansion project. The original scope of the project, utilizing the idea of using 1,000 PSI as a limiting factor, because that's what many off-the-shelf piping components were, dictated that we'd need to have 3 forwarding stations for that expansion. The graphic on the right shows what you can see, the blue line on the top right. That was the projected effective envelope using a 1,000 PSI pump located at our 5,000 sand plant. I believe you probably be able to see that located, denotated as 550 SP on the left side of that graphic. Understanding that 3 sand plants at multiple $1 million a piece, if we could reduce that, we would be able to increase the efficiency of the overall operation, decrease our capital expenditure. Everything at that point was entirely conceptual. As we move forward, we for multiple reasons, relocated a GEHO pump, which is a ZPM 700 that we'd procured for another sand plant, to the 5,000 sand plant. The nameplate on that pump was 1,700 PSI versus the 1,000 PSI we had originally modeled everything on that, modeled the Blitz expansion for. So using 1,700 PSI generated new backfill envelopes, and that initially indicated that we'd be able to remove one of the plants on the Blitz expansion. We retained Patterson and Cook to serve as a peer review to evaluate the model, to identify discontinuities or discrepancies. What they came back up with their numerical models versus what we had measured in the field for our field models showed a very close correlation, and did confirm that we would be able to move the Blitz sand plant number 1 farther east and higher in elevation, closer to the envelope, so we'd have a better optimization and utilization of that plant. First step on doing that, though, being that we were going to be designing a pipeline around a 1,700 PSI pump as opposed to a 1,000 PSI pump, we had to go back and look at the design parameters for the pipeline itself. Did a lot of work with Victaulic, being that the pipe was going to go from the west side of the mine underneath the Stillwater River on our 4,400 level, and then back up to the new east side plant. We were going to be seeing pressures far in excess of 2,000 PSI if we did have a event where the pump did pump to the maximum 1,700 PSI. So we did a significant amount of engineering, again, retaining Patterson and Cook to review that design, and through the installation of everything, we were able to successfully deliver sand to the future location of the Blitz sand plant in February of 2017. That served as the first phase gate for the project, in which we did prove that we could pump sand very effectively to where the Blitz sand plant was. It matched the correlated models between Patterson and Cook and our internal model to a degree of about 3%. So very satisfied with that. That sand line that was then in place served as the production sand line for Blitz from 2017 through 2019 at the point we commissioned the new East Side plant. As we moved into the actual design and excavation of the plant, we retained Nordman Engineering to help with the structural designs, the pumping systems, full civil, mechanical, and electrical designs, along with instrumentation and control. The graphic on the right is a high-level overview block model of what the plant looked like from a design perspective. It's a picture of the 5400 East plant. The plant was designed to have 3 discrete outputs, one pump that would pump to a stope, a pump that would be able to pump to a forwarding station for the Blitz sand plant number 2, and then a third discrete output, which in the future is planned to be cemented sand. Knowing the design size and capacity of the plant was evaluated based on both the mine plan along with asking the what if of what could possibly be the needs in the future. And at this point, now that we're a couple of years beyond the design and through the commissioning phase, we're glad we asked those what ifs because we were already eating into those what ifs. We did also have many conversations with the existing plant operators, from both the west side of the mine and at other locations as well, get their inputs from what's worked well, what hasn't. Did a exhaustive site study, seeing the benefits, where the downtimes are, what the operational efficiencies and bottlenecks are to try and eliminate those as we move forward. We did go through, when we identified what the constraints of the plant were going to be, we did a significant diamond drilling program to understand the geology to make sure we weren't going to be putting the plant in an area of poor ground. Once we had the design finalized, Stillwater Mining development crews moved in. Initially, they did the excavation on the 5400 level. It was about 1,800 equivalent feet. The excavation did include all the required infrastructure, such as the master control center, floor sumps, the ventilation crosscuts, silo excavations, accesses. The plant itself, the main plant itself, is about 180 feet long, 18 to 20 feet tall, for the placement of an overhead crane. Again, this was all done by Stillwater crews, took about 8 months for the excavation. The crews at another Stillwater Mining crew concurrently planned for a finish-on-finish scheduling. Mine the 5600, where the top of the silos were located. So the graphic on the right shows what the top of the silos, which are located immediately above the lower plant. About 1,500 equivalent feet was the access for the six raise bore locations to bore the silos, along with the ventilation silo, a main sump for catching silo overflow for that water then to be recirculated back into the backfill system, and then the location of a future sand silo or cement silo for cemented underhand fill. Upon completion of the excavation of both the top and the bottom, the Stillwater Mines raise bore crews moved in, initially boring the ventilation hole, which is a 5-foot by 200-foot long hole to allow flow-through ventilation for both the lower plant and the top of the silos. They then moved over to excavate the 10-foot diameter by 195-foot long silos. This was the first significant project delay that we had due to equipment failure and breakdowns. The team continued to move ahead. Once the raise boring was completed, we solicited a contractor to come in and apply 3 inches of shotcrete to the interior of the silos for the longevity of those excavations. Through the whole process, worked with numerous different engineering groups. The engineering groups consisted of Nordman Engineering. Again, they issued the 4 construction drawings, the civil, mechanical, electrical, and control designs. Significant work with Patterson and Cook. They served as the hydraulic review for the sand delivery system, both to the plant and from the plant moving forward. And we are also working with them on an underhand quality fill design. We have moved beyond the feasibility study and are now initiating a pilot test program with them. A lot of work with Weir Minerals, with the pump selection, pump sizing, and then again with the Sibanye Stillwater engineering team, both on the project management side and then just leveraging the expertise and experience that our team in-house has to bring this this project into fruition. The overall project flow on this, we brought all the design components to about a 60% IFC level. So just beyond the feasibility level, at which point we did begin the excavation. More or less concurrent with the excavation, many of the items did have a long lead procurement time. So we did target just-in-time procurement within this project. We didn't want to have materials sitting on hand, sometimes up to a year potentially before they were ready for installation. With the delays we did have some material time on site that did create a heartache and a trouble with as we were moving forward, in part due to the fact that we were doing part of the construction during winter. So parts that were stored on surface got covered with snow, and it took significant time going to find those at a later time. From initiating procurement at the end of excavation, we started the civil construction with the installation of concrete flooring, shotcrete on the ribs, steel construction, and then we moved into the mechanical installations of pumps and piping, and then followed with the electrical and control installations. Commissioning consisted of testing each individual component and subsystem, and then rolling the subsystems into larger systems testing, and then finally progress in project debugging. As with any project, the biggest thing to take away there are the lessons learned, because we will be doing projects in the future, and don't want to let any lesson learned to go unchecked and unshared. So the biggest lessons learned that we had to take away from this project was avoid changing project managers mid-project. This project had a total of 5 project manager changes within the course of it. 3 of those project managers were myself, where I started and then was handed off to somebody else for numerous reasons, then taking it back over and then handing it off again. It creates much more continuity if you can have the same project manager throughout the course of a project. Do employ just-in-time delivery of components, and then if things do arrive early, lock them up in a safe location where either snow can't cover them or they can't grow legs and walk away. In a lot of mines, the typical mantra is buy 3, 1 to take, 1 to break, and 1 to use. So lock it up so that way you don't have to worry about them walking away. Clearly identify project resources and the resource capabilities. Doing such, make sure that the expectations are clear and are realistic for the work that's going to be being done. Next, slow is smooth and smooth is fast. Take the time to make sure the installations are done appropriately the first time through, and then then making sure we're utilizing contractors appropriately and applying appropriate quality controls to make sure that's being done appropriately the first time, minimizing rework and overall accelerating the project. And then finally, having the right people present at the right times. No, this was a very quick overview. I would like to give just a tremendous thanks to all the various teams that were a part of this. And with that, I will open it up for any questions.
Well, thank you, Bracken. We haven't had any questions posted, and given some of the technical challenges we've encountered this morning, probably best if we move on. So thank you for your time. Very much appreciated.
My pleasure. Thank you very much, Mick.
Our next speaker is Chris Leatherman. He's the mine and development manager at Bayer Crop Sciences. Chris grew up in Salt Lake City, graduated with a BS in mining engineering from the University of Utah. His first job was with Phelps Dodge at the Chino mine near Silver City, New Mexico. Chris then relocated back to Salt Lake City and worked at Bingham Canyon Mine for 10 years in several technical and operational roles. He's worked at Monsanto Bayer for 15 years, managing mining operations and leading mine permitting, development, and remediation efforts. Chris, I think the floor is yours. Thank you.
All right. Well, thank you very much. Look forward to the opportunity to spend a few minutes with you talking about the permitting efforts we completed last year in realizing the record decision for a 40-year phosphate mine here in Southeast Idaho. Just to touch base a little bit on who I work for. So I'm with Bayer Crop Science. For myself, until a couple of years ago, I used to know Bayer as the aspirin company, and they are now the owner and operator of our mining operation and plant up here in Soda Springs, Idaho. Bayer's got 3 different divisions. There's consumer health. You might recognize some of the names there of the products that you might have used or see at the store. There's a pharmaceutical division. And then most pertinent to this conversation today is the crop science division, which contains crop protection, seeds and traits, and also digital farming. The biggest portion of that came from the 2018 buyout of Monsanto, and that brought Bayer's portfolio in crop science up to where it is today. And it might be interesting just to note that Bayer's only mining interests here in southeast Idaho, with it being an international company of about 120,000 people. So in Soda Springs, we've got different phosphate mines. We basically deliver, process the ore, and then from there we have two different processes at our phosphorus plant, Soda Springs. There's a beneficiation process where you can see a kiln. The ore is fed in raw and comes out as a nodule, and many of the volatiles are burned off, and the ore is concentrated in that process, and then it's put into a furnace. And in the furnace, the ore, or the phosphate, is then comes off as a gas, is then condensed, and then is shipped off-site as elemental phosphorus. And eventually at other locations, it's formulated into glyphosate, which is the primary ingredient in Roundup. So to give a little bit of context to a few things I'm going to share here in a minute, I just want to touch base on a little bit of permitting history for Bayer, previously Monsanto, here in Soda Springs. You can see a bunch of different mines. The ones that are depicted in yellow are historic mines starting back in the 1950s. Green is the current mine, which is Blackfoot Bridge, and then the ones that we have ahead of us are in pink. More specifically, Caldwell is the one that we realized the record decision on in September of 2019. Just kind of want to point out in contrast, about 20 years ago, we realized our authorization for the South Rasmussen mine. You'll see that that took about 2 years and cost less than about $500,000. 10 years later, we received approval for our Blackfoot Bridge mine. You can see what you could almost describe as an exponential change in that duration and cost, where it went to 7 years and about $13 million to realize that permitting. And we had some anticipation of subsequent changes in how much cost and duration it would take to get Caldwell approved in about 2019. Unfortunately, we were able to come in with that approval being less than the time for Blackfoot Bridge by about 1.5 years. And the cost was incrementally a little bit higher, but it was pretty much on par for Blackfoot. And all that came with it being a larger area, more resources that had to be evaluated, and also being permitted under increasing regulations. So just want to talk about a few things that happened to make it possible for us to realize that approval in a more timely and a fairly consistent cost manner than Blackfoot Bridge almost 10 years earlier. So the strategies I'm just going to touch on for a few minutes are broken down into 3 buckets: regulatory approach, mine design and layout, and then public and government outreach. I don't think anything I'm going to say here is going to be of any new breaking news, but the application of these strategies helped us to realize a very favorable outcome. And I hope as I share them, there might be something that perks your interest or something that you might be able to apply in your business and with maybe the NEPA work that you have going on. So first of all, regulatory approach. As Bracken mentioned in his presentation, we took a step back and applied lessons learned from permitting of the Blackfoot Bridge mine. That was the first EIS that Monsanto at the time had gone through in permitting a phosphate mine here in southeast Idaho. And we learned a lot from going through that process. The standard business fare for getting a mine permitted was to go to BLM and pretty much submit a mine reclamation plan and tell them of, notify them of your intent to develop the project. At that point, they would start with the baseline studies, and then they would move into NEPA and so forth. We wanted to do things a little bit different. So we started looking around and noticed in our neighbor in Nevada, BLM had a 3809 plan of operations process. And more specifically, they had an instruction memorandum that emphasized a pre-plan of operational component of that process. And so what we did is we we learned about that, and we went and started advocating that type of process with the local BLM staff. And after some education and advocacy, they agreed, along with some cooperating agencies, to give that a try, and essentially gave us, as a proponent, the opportunity to submit more of a scoping document as our pre-plan of operations submittal. And that kind of laid out the premise of the project, our intent to develop it. And that was a trigger mechanism, much as submitting a mine reclamation plan would have been under the current process that they were doing. That gave us the opportunity to realize a couple things. First of all, we were able to then sit in the driver's seat. I think being able to be a little bit more agile and efficient, and also we had more of a vested interest. We were able to gather the baseline data that was needed, and that helped in a couple ways. One of them was we were able to get through that process faster. We were able to do so by having plans of study that the agencies agreed to, so they were getting the data they needed for their NEPA process, and then we put together the baseline reports in which they approved. And then we also realized the benefit of being able to collect data and basically develop our mine reclamation plan concurrent with our baseline data collection, informing us as we went along the way, instead of discovering things after the fact that we wished our mine design and layout would have been a function of. And so there were some upsides from all of that. Second of all, we tried to lead the NEPA process by obtaining the relevant permits beforehand instead of concurrently, or perhaps after the fact. And just two examples are, here in Idaho, we have a point of compliance determination process for groundwater from the Idaho Department of Environmental Quality. And that was something that we obtained prior to actually getting into the NEPA process. And that gave us a chance to really kind of put some sideboards on what BLM had to look at. And so once they really got a NEPA, they didn't have to spend a lot of time worrying about groundwater, because the relevant permit for that had been issued, and DEQ had already addressed that. And so that was something that BLM didn't have to be distracted with, and it was kind of off, on the checklist of things that have been done. Similar story about a 404 permit with the Corps of Engineers, and having that taken care of, and having that also provide similar benefit to the point of compliance determination. So we try to make sure that NEPA was being led by those permits. And then we finally went into submitting our mine reclamation plan. Once again, we felt like it was much more informed because it was being developed during a 3-year period in which we were collecting baseline information, and we also were able to get new information from additional geological studies we were doing as such. But we really tried to make sure that the mine reclamation plan was as comprehensive as possible, having looked at all the different scenarios that perhaps BLM or another agency might look at in the NEPA process. And then we actually included an appendix to our mine reclamation plan with options that we as a proponent had considered and had dismissed, and we provided data and reasoning as such. And I think that helped a lot for NEPA, BLM, when they're in the NEPA mode, because they had to look at different options. And when they went to look at that option, they could refer to that appendix and realize that we had been there, considered that, and it gave them backing and helped them to move through that alternatives consideration much quicker. That did cause a little bit of stress for a few individuals because they kind of had the mandate that they needed to have an alternative at the time they published the draft, but things fortunately worked out such that they had a viable alternative by the time it was done. So second of all, mine design and layout. I'm just going to preface this section with a little bit of a story. I worked very closely on this project with a mine engineer that's closing out his career in a few years. He's close to retirement. He said early on in his career, he was given the mandate to pretty much make sure that he made a mine design and did schedules and layouts that reduce costs as much as possible. And I've worked at places where, I've seen the effects of that. And as we went into developing this mine reclamation plan and proposing this mine, we tried to balance our environmental considerations with others such as cost. And oftentimes those considerations did result in a higher development cost, and in some cases they'll actually result in a higher operational cost once this mine goes into production in 2024. But we saw a lot of benefits and upsides by doing this as we tried to value environmental and other considerations along with maybe some of those simpler things such as cost. One example is this area is somewhat remote. We as a company have hauled ore down to our plant for about 70 years by truck. We would have had to put in a 10-mile haul road with a lot of disturbance crossing areas that had wetlands. And so we opted to develop a much shorter road to a rail spur that's in the mine area. Another environmental consideration that we made as we put the mine plan together was to avoid as much as possible sage-grouse and habitat where this mine is on the fringe of a general habitat area. We also tried to make sure that our mine layout was informed by baseline data. We had conceptual design, as I mentioned, with that pre-plan of operations process. One example of how that mine design was informed was through a cultural resource survey. We learned that there was an area that we had a haul road tentatively planned that would have gone over an area of pottery shards and Indian artifacts. And so we rerouted that. And we also learned more about the importance of the ecosystem around a creek that the mine would have gone through. And so we're leaving ore behind and stepping or mining up to and stepping over that creek and then continuing with the mine development. And then finally, we sought opportunities to try to reduce impacts to the environment. That happened in the form of one example is the picture you see on the left. There's an open pit that has been reclaimed as part of the approved mine reclamation plan for that former disturbance. But we have an opportunity to reduce our footprint by hauling overburden to this open pit and further backfilling it. Once again, that does come at a larger cost, but provides a lot of upside for this prior impact and also reduces our impact and potential legacy problems with the mine in the future. Then finally, government and public outreach. We really had a couple goals. We wanted strong stakeholder support, and we wanted to make sure that we had no litigation. And I'll loop back to both of those. So, unlike Blackfoot, we started ramping up and realizing that we were going to need to get people to weigh in at the time of the draft EIS and provide comments for the final EIS and those sort of things. And that wasn't the right way to do it. So with Caldwell, we started early and we tried to consistently maintain our outreach to our various stakeholders. And so even during the scoping time, we brought in NGOs, we visited with community members, we were reaching out to government, and we started to share with them our intent to develop the mine and all the things we were trying to build into the mine design, all the considerations we're making to make this a very environmentally sustainable mine going forward, and how it would help to avoid many of the legacy issues we'd seen in the past. And you can see that advocacy went across a lot of different venues. We had a public affairs gentleman that was associated with this project, and he joked at one point here in Soda Springs or larger Caribou County, if 3 or 4 people were gathered together, they better watch out because somebody was going to talk to him about Caldwell. And while that was a joke, it's kind of felt that way. We actually scheduled and went to 100 different venues, whether it be a county commission group or a city council or a library or a Kiwanis club, or going to fairs and trying to talk to the public at fairs. We even had different vendor meetings here locally where those that were providing services and materials and those sort of things to the local mine and plant, we had a chance to inform them and ask them to weigh in. So did a lot of work in that area. And coming back to the goals, 2 things I think signaled that whole advocacy or outreach went well for us was the fact that we saw in an article around the time of the approval of the mine, one of our strongest NGOs, a member of that NGO, was quoted in an newspaper article saying how Bear had taken into account their input in the design of the mine, and so that felt really good. And also, we made it through with no litigation on this mine approval. And the two previous mines here in the local area, phosphate mines, one of them, they didn't go to litigation, but there was some definite bumps and issues that came up. And the one prior to that, there was even some threats to suspend development of the project as that was in court. So it was nice to avoid all that and to have a good approval that everybody was supportive of. So just to kind of wrap things up, I think it's important to recognize that we have some favorable circumstances. It seems like when you have a big multi-year project like this, like I said, it was about 5.5 years, you do have some upsides and you do have some downsides. And in this case, two favorable circumstances or upsides occurred that I think also came into play. You know, once again, just want to contrast our Blackfoot Bridge mine, $13 million, 7 years, 10 years later with increasing regulation, and applying these strategies, we were able to mitigate the timeline to 5.5 years, and we were also able to realize it at a very similar cost to get to that record decision. Two things I would say helped out was early on, BLM and the cooperating agencies on this project gave us an opportunity to participate in the contractor selection. We weren't a part of the final decision making, but we were allowed to listen in and participate in the vendor presentations. We were able to visit with agencies about things we thought were things that each of those third-party contractors would bring to the project as a positive type thing, and they made the selection, but we were able to benefit from a good third-party contractor, and I think it helped that we were able to weigh in on that selection. And then finally, I think a lot of you are familiar with and probably heard about, you know, the Trump administration, the executive order that was issued in 2017, and then on the tail of that was the Department of Interior Secretarial Order 3355. And for me, this is largely about the page count. It's about the 1 year sort of NEPA mandate. We were heavily into NEPA at this point. So those things kind of resonate a little bit on the project, but the thing that was really positive for us is we saw a tangible difference in the engagement that we were seeing from BLM. Not to say that they weren't doing a good job, but there became an increased urgency on their part to get this to a final EIS stage and then to get a ROD issued. And so we are grateful for those orders and the subsequent response that BLM and the local staff had to those. And I believe that we would have gone longer than that 5.5 years haven't it been for these favorable circumstances. So, like I said, probably nothing new or earth shaking, but consistent application of these three strategies and then not realizing favorable circumstances, I think really helped us to realize a mine approval in a time where I've heard and I've read that a lot of NEPA mine approvals for mines can take upwards of 10 years, if not longer. And the cost of those can be extraordinary, and we're glad to be able to see, doing smart things help to mitigate the time and the cost to bring this mine online. And we're duly excited to the fact that since it's a 40-year mine, we won't be having to do NEPA in the near future. So that's all I've got. Thank you for your time.
Chris, thank you. Very much appreciated. And I think we'll move on to Joe. Time's a little tight, Joe. Hopefully we can squeeze it in. Let me get over to whatever. So our next speaker is Joe Brinton. Joe has a BS in engineering geology from Brigham Young University and an MS in structural geology from the University of Alaska Fairbanks. He's worked for the BLM, USGS, U.S. Forest Service, various geologic consulting firms, and an oil field services company, and a drilling company. Joe's international experience comes from living in Ecuador for 2 years, Brazil for 4 months, and traveling throughout Mexico and Central America. In addition, he's an active triathlete and plans to finish an Ironman distance race next year. To keep this goal alive, he works year-round to maintain good physical condition, spends his free time rock climbing, mountaineering, backpacking, scuba diving, and spelunking, and it wears me out just saying that. Joe, welcome. Thank you. Look forward to hearing what you have to say.
Okay, so I'll start up this PowerPoint right now, and we'll see if it works. And it just might work. Okay, can everyone see the PowerPoint? I guess so.
Looks good.
So this will be a pretty big departure from the previous two talks. I hope you enjoy it. It's something I did a few years ago, and I think it's pretty interesting. So we've already been over who I am. We don't need to do that. The company that I worked for this project was Resource Capital Funds. They're based in Denver, a private equity group that focuses on mining. And we had coal as our target. Thought that was a little bit underserved in the exploration world. So our goal was to become an exploration company for coal in particular, especially in places where local jurisdictions couldn't clamp down on the transportation issue of coal. So Greenland fit the bill. Looks like a pretty nice place. A brief, I'll real quickly describe what Greenland is. Everyone's heard of Greenland, and it's mostly ice, and instead Iceland is mostly green and so forth. The country of Greenland itself is about the size of Europe, but the population, as you'll note here, is 60,000 people. So that's like Harriman plus half of Riverton, all spread out on a landmass the size of Europe. So pretty sparsely populated. As a landmass, about 80% of it is ice, glacial ice that's just there. And then there's 20% of it that's not. It's just, you see exposed ground in the summer. So that 20%, that ends up being about the size of the country of Peru or the size of Sweden. So again, it's a big country, but even though most of it's locked up in ice, there's still a lot of country to look at. Of that 20% that's not ice, most of it is igneous rock, metamorphic rock, very old Archean basement rock. But there is a little corner of sedimentary rock, the coal-bearing kind of Cretaceous rock, like we have in Utah. So there has been mining in the past. About 100 years ago, they started a little mine, and there's some pictures of the remnants of the old mine. So there has been coal. In 1982, the country of Denmark decided to explore to see if there was potential for more coal mining to be done there. They did an exploration project on this area called the Nuswak Peninsula. They drilled a few holes, did a little bit of field mapping, and decided not to do anything about it. So 30 years later, that's when Coastal Ventures was formed, and we decided to take up where the country of Denmark left off. So our exploration license area was 6,000 square kilometers, a pretty big area. Just to put that in perspective, in Utah, for example, this area highlighted in red is the Wasatch Plateau and the Book Cliffs coal fields. And all together, all of that country is about the same amount of area that we were looking at in our exploration license. So a pretty big landmass to look at. Our two exploration objectives were to validate the previous work that had been done and then expand the geographic area of the known coal resources. So to do that, we had detailed field mapping, meaning boots on the ground, basically, looking for any outcrops of coal and then identifying good drill locations. And then phase two was the core drilling itself, to do some diamond drilling and to define the resource a little better. And highlighted in red is that the total absence of roads meant that we had to use a lot of helicopters. And by total absence, I mean total. There was not one single road anywhere in this whole area. So how do you do that? You load a whole lot of stuff into a very big helicopter, and you fly out to the tundra and you set up camp. And then you hike, and then you sample, and then you hike, and then you sample, and then you hike. That one might remind people of the deer hunt. And then you sample, and you hike, and you load all your samples into a helicopter, and then do it again. So we spent an entire summer doing that. Oh yeah, here's a good slide. So if you can see, if you look close, you can see the coal outcrop. As you're flying along, you could see that probably is a coal outcrop. So in order to collect a sample there, we found a spot down here where we could land the helicopter on the glacier and hiked up the terrain. And I was able to get up and measure the thickness of the section and grab a sample of that particular coal bed. All told, we were able to map around 280 square miles on foot. And overall, it was about 7,800 vertical feet of stratigraphic section that we were able to map. Then we moved on to phase 2, which is drilling. So in order to drill there, we had to ship our equipment from Colorado to Virginia by train. And then from there, it was on a big boat to Asiat, Greenland, and then transload to a smaller vessel, and then transload to a barge, and then from the barge with a helicopter to the drill site. So here's a picture of transloading from the big boat to the medium boat. And then from the medium boat, you can see right in there, there's a smaller barge. And then from the smaller barge, we could pick it up with a helicopter and take it to the drill site. So yeah, a lot of steps involved in getting from point A to point B. There's the helicopter coming in. So drilling in Greenland had 6 particular challenges that aren't very common anywhere else. And so I'll go over these in detail. I have them listed here, but we'll look at them in detail next. It's pretty ironic that the country that holds 60% of the world's fresh water, we still had problems getting water for drilling, primarily because water in its solid form doesn't help us much. It's liquid water that we need for drilling. And most of the water in Greenland is in its solid state. But even at that, the terrain itself didn't lend itself to holding back water. So there weren't any real puddles or ponds or streams or natural features where we could have pumped fresh water from. Sometimes it was up to 10 miles between places of standing water that would have been useful for drilling. In this picture, you can see, if you look close, a big long pipeline. That one ran a half a mile. That's the closest we could get to the nearest source of water. And yeah, endless challenges trying to keep water flowing in the cold weather for long distances like that. We also experienced some methane experiences on the island. Some of the coal itself had generated methane because there's permafrost in the area. That permafrost acts as a methane trap. So we had to employ the same techniques that they use in oil and gas drilling, namely blowout preventers and flare systems and the whole 9 yards, just to be able to drill little tiny core holes. Here's a picture of the blowout preventer that we used, a big oil field style blowout preventer, just for little tiny core holes. We had to go oil field style. Also, in this area, there's been some lava flows in the last 10,000 years. One thing about lava flows, when they cool, a lot of times they leave columnar joints, which are just a high density of vertical fractures. And these cause trouble for drilling. They make it very difficult to maintain circulation and to maintain the straightness of your borehole. The only thing that is harder than drilling through lava flows is drilling through glaciated terrain. After the glacier comes through and it drops off all of the sediment that it picked up, it's just a big rubble field. And again, drilling through the rubble is extremely difficult. But you probably won't find a more scenic place to set up a drill rig. Yeah, until the winter comes. This was our attempt at trying to stay warm. We had a parachute strapped on the top of the mast to try to keep some heat in. And one night the entire parachute blew away and we never found it again. So some challenging conditions for sure. So here's some numbers. All told, we were able to drill 2,350 feet in the summer of 2014. And all told, for the cost of the camp and the transportation and the helicopters and the drilling, it all came in at about $3 million. So more or less, we averaged about $1,500 per foot of drilling. just as a reference, some exploration work I've done in Utah, it'll generally cost around $60 a foot. That involves all the casing, that involves all the water transfer, all the permitting, all of the pond reclamation. Everything is a lot cheaper in Utah than in Greenland. Even if you have to use a helicopter, as you do in some places in Utah, it adds cost, but still nowhere near the cost that we experienced in Greenland. As a typical rule of thumb in the oil field, they'll budget $1,000 per foot for some of their exploration projects. So it even costs us more than your typical oil and gas exploration project to do some drilling in Greenland. Also, there are a lot of mosquitoes. Anyone that's worked or lived in the Arctic has probably experienced the swarming of mosquitoes, and that's what we had to do, had fun with there. So here's the results. We did find a pretty big coal reserve, 2.3 billion tons in potential resource. 10 million tons are of what we classify as measured resource, meaning that it's within a half-mile radius circle of a known coal exposure, either from their drill hole or from an outcrop. Then there's 100 million tons of indicated. Indicated means that it's within a 3/4 mile radius. So from the same points that we drilled and measured in outcrop, we could augment the amount of potential coal resources as part of the indicated category. And then 1.1 billion tons of inferred, and inferred meaning it's within 6 miles of a known point. And then the 1.2 billion tons is hypothetical, meaning it probably exists, but there's no evidence within 6 miles to prove that or indicate that it's there. So from a mining point of view, in case some of you may not be familiar with the way coal works, a 10 million ton reserve is not even really worth trying for. By the time you get 100 million tons in the reserve, then it's probably something worth doing. And 100 or 1 billion tons would definitely be worth looking at. So how does this coal that we found in Greenland compare to the coal that you guys have in Utah? In Greenland, it's sub-bituminous coal, whereas Utah is bituminous. So just a little better rank of coal in Utah. The BTU per pound is a little higher in Utah. You can see 16,000 BTU per pound in the typical Utah coal versus the 14,000 that we found in Greenland. Again, this is with ash in it, so a little lower numbers there. The ash content itself is a little better in the Utah coals, 7 to 9% versus 9 to 13% in Greenland. And sulfur values, again, we're just a little higher in Greenland than they are in Utah. Neither of these coals are coking coals. Everyone always asks, is it metallurgical coal? And it's not. It just does not have the right characteristics to be qualified as metallurgical coal. So the pros of mining in Greenland or exploring in Greenland, or at least thinking about starting a mine in Greenland, is that the reserve is very big. The coal is not the best in the world, but it's not bad. It's pretty average. And you're in a great position to ship your coal. In coal itself, I mean, shipping is kind of the big deal because it's a bulk commodity. Shipping